Okay.
Okay. All right. So you can see my screen, right?
Yes.
So this is this presentation is on the simulation I did on the comparator circuit from the paper. So the comparator circuit is taken from the following paper mentioned here. So the dynamic CMP schematic, this was the left hand side circuit was from the thesis from Yogesh Kumar Ramadas that we did simulations earlier in the spring semester, and then this is the comparator circuit in the paper we are working on now. These two comparator circuits are actually the same, even though there are some extra MOSFETs in the first one. These two circuits, the comparator circuits, are actually the same. So what is our task? So our task is related to this TVSA, the total delay time, which is the sum of these two delay times. T naught is the delay due to the capacitor discharge, and basically, if we see from the graph, T naught is the time it takes for M2 to turn on, and T latch is the time it takes to M1 to turn on, and TVSA is the total time. It's not a time gap, it's a total time. I'm sorry. That is a total time between these two MOSFETs turning on. And so how do we measure this TVSA, this delay time? We measure it by measuring the time gap between when Vn, the negative input, turns on, as we can see here the time turns on, and Vson, which is the negative output, reaches half times VDD. So this time gap over here, as you can see, is TVSA, and our job in this task was to show the relation between TVSA and these three voltages: V induced, VDD, and Vn. So this was the data that I got so by simulating. So what I did is that I took four cases. One is this VDD equals to 2 volt, V delta Vn equals to 70, 10, and this for four cases I measured TVSA for different V induced, and this was the graph that I got. I have also included the graph actually included in the homework slides just for comparison. One interesting finding is that after V induced exceeds VDD, after V induced exceeds VDD, the TVS actually increases. Before exceeding VDD, the TVS decreases, as you can see in these two graphs. For these two graphs, VDD was 2 volts, so V induced is actually less than 2 volts. So actually, we can see that the TVS is decreasing. But in these two, VDD is actually 1 volt. So once we exceed the 1 volt, we actually see the graph starts to increase. So this is the similar kind of trend that we see in this graph as well. So here, so yeah, that's presentation. Thank you so much.
So you apply higher input voltage than VDD?
No, I just said that like when V induced it becomes V induced is less than VDD, TVS decreases. Once
can you send your PPT to chat?
Oh, sorry, I didn't do that. I forgot. Oh, I applied more voltage than VDD. Yes, I did. I shouldn't have.
So send the PPT to the chat. Zoom chat.
Yes, I'm doing it. Give me a moment. Okay, should be sent. Find the Zoom chat.
You see my screen, right?
Yes.
So in the paper, VDD is 1 volt here, so V in they stop at 1, right?
Oh, but I did not stop at 1. I continued.
So you give more than VDD input. So
Yes.
you can see VDD is here, so you apply more voltage than VDD.
Yes.
So VS V input here if larger than VDD, so VGS means 8. I think in simulation is still work, but in your circuit, it might your chip might die because you apply higher voltage than.
Yeah, I see. I did not. I just okay.
So in simulation it still work, but in the real circuit, your chip might
It
die.
will not.
No.
Okay, understood.
You can see the trend is almost similar, but the delay is much higher than their work, right? Isn't it? In here there is like this graph 0.6 input, and here is yours 500 picosecond, isn't it? Here is picosecond. In the y-axis, it is picosecond.
Yes. It's a picosecond. Yep.
Here is those 130. So,
But for oh yeah, for the VDD is equal to 1 volt. The values are really, yeah. You can go to the previous slide. Actually, you can see the data there.
where? What?
In the previous slide. You can go to the previous slide. Yeah, you can actually see the values I got.
So what I did here, right? My simulation is this one.
Yeah. This is the value you actually gave. So this is the
270 milligram. So this is line, and how much?
actually those two are actually all right, because 0.6 the graph actually really goes up. Yeah.
And VDC.
In fact, in your graph, for 1 volt VDD2 and del V70, the value is not 164.
What?
In your graph, the VDD goes to 2 volt and del V70. The bottom
Yes,
graph.
you should
For 1
right?
volt, it should be 164, right?
So my simulation case is V in DC is 1 volt, right?
Yes. But for this, the TVSS should be 164. We did this.
So it's almost double. In here is
Yeah.
about 70. So
Yeah.
So your other values is my double, like here 80. Here 200 and here about 100, 1.4, 5. I think it should be okay because in the paper and it's really old paper, so the process is different from our process, I think.
I see.
In here they use this process. Our process is 180 nanometer process, right? It is different. It's different process. I think we only compare the trend, but the value is might be much different. Okay.
Okay.
Hi, can you share your screen?
Yeah. Do you see my screen?
Yeah.
Yes, I have just the simulation, but the time delay is different. It's very high.
Compared to Ryan.
Yes, it's the when I push the value like this, with the VDD2 and the delta voltage input is 70. The time delay more
The
than
variable names are
5.
different actually.
Yes. But I compare with Home, it more than 100, but
No,
with
you should in not here, but different. In the raising at
is this?
it is raising at a clock.
Yeah, now it should be
Yes,
all right.
it's raising as like this.
Yeah,
Why
it should be all right now. Yep.
But the delay is more than 500.
why is
But when I use the simulation file from Home, it's just more than 100.
so here is the circuit you make?
Yeah. Yes, I make by myself.
Did you compare your circuit and my circuit?
Yes, your circuit is true, but my circuit is more delay.
Can I share your team viewer?
Okay. Can you see it? Oh, I can. Okay, I can copy to you. Chat.
Okay, I see. Where? Yeah, the circuit you make?
Yeah, yes.
Where in my circuit?
Okay, we open this. schematic. Yeah, this circuit.
Did you compare all? It's similar. It's the same.
Yeah, compared to length width and CMOS and PMOS. The logic of output N and output P is a true. It just have a problem with the delay time.
Where delay? You take delay in here? Did not?
No, it's it here. I check this.
Yes. SON, right?
Yeah.
Yes. In this, the log also is same.
Yeah, it's the duration is the 2 and the time for one true and the 0 is one micro.
But animal, the clock, your clock
Yeah,
is
in
here is 1 picosecond.
oh picosecond. Oh, one.
It's still fixed, right? You did not run.
This I sometimes have a problem. I think it's we close and open again.
Because your directory here is wrong. When you copy my schematic, so just not it. Formatted block.
To micro.
Why here 1 nanosecond?
Oh, it's
It's wrong.
it's not raising edge.
All right.
Yeah, it's true. I have done it
Why?
last morning.
Why your circuit is very more delay?
Um,
Too strange.
I check a lot of time every every parameter, but it's different.
Why is the circuit? How about comparing on node? So Compare this note.
Bro, I have a question.
Yes. Yes.
The time I used in this either 20 is its effect the result output.
Which one?
I use the 220 micro in the transistor. It is affect the result.
No. So you can see the delay is almost the same in every rising edge, right?
Yes.
So the time you simulate doesn't affect.
Okay.
Compare this one with
The difference is does are you more hot with this effect?
what?
Yeah.
What?
Sorry. Is the are you put output P like this?
It's not
Is it
important.
effect?
No. No.
Okay.
Can you make a couple of clock?
Sorry. Okay. Okay.
Style clock. Yeah. Oh, it's different. So your circuit should have some problem, right?
Yes.
We simulate in the same condition,
Yes.
but I think should be something wrong in the circuit. Difficult to find. Your difference is here is 5 micro. Here is
Oh,
500.
sorry. Oh,
Oh, why?
oh, sorry.
We should look very careful.
But I saw in the circuits in the paper it the 1.5 divide with 1.5. Bro,
Hmm?
the parameter
Maybe
I saw in the paper.
now is the
Yeah.
same, right?
Yes.
So in the paper, where the paper?
Sorry. Okay, let me. um, Okay. Yeah, I saw it's a 1.5 divide 1.5.
So it is my mistake. So
Oh,
your
okay.
circuit is correct.
Yeah.
Uh,
I spent this afternoon to find problem, but I cannot. Sorry.
okay, 0.5 and 5 look. So in the schematic, easy to see, but in the cadence is quite difficult. So
Yes.
next time you should look at here.
Okay. Okay.
Look at here is easier to see.
Okay.
Okay. When you look at here,
Okay.
it's a little difficult.
Yes.
So next week, next week homework is Hayden. Ryan, are you here? Hey, Ryan.
Yes. Yes, 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 yes. Hello, can you hear me?
Yes. Yes.
Okay, so the next week, what should I do?
Where buck converter?
Chapter 4.
Is the below is the what 4.7. Yes.
Where pen?
When they're home, when are you coming to Korea?
What?
Is the
Sorry, well, Thai. When are you coming to Korea?
I think it's the end of the August.
Ah, okay.
Yes.
Before the
Okay.
semester, then
Yeah, I will come when I got the visa.
I see.
Okay.
So you guys already make comparator, right?
Yep.
You also make this buck converter.
Yeah. Yes.
Yep.
So now you have to make this first next week. This is
Okay.
easy. So
It's happen later.
only put some register and just quit. Here is a speed mode. Okay.
Okay.
So
Or I'll just record it. Okay, I'm recording it.
so speed mode is your register you made. In here, rectify voltage is from 2 to 5. So you can use this PMOS, right? PMOS
Okay.
2 volt.
Okay.
But
Register is where register.
Okay.
Register here. So you can use this register.
Okay.
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 why do you change the value of the register?
Yes, you put in values here, resistance.
Ah, okay.
22 mega ohm, 16. You make this letter. Okay.
All right.
Okay.
Reference is just DC. In DC
Do we need to
voltage.
simulate this or just making this would be enough?
You should simulate it. You change reference voltage, right?
Okay. The
You
VREC.
change reference voltage and you change VREF. So
okay.
in here, here is bit, right? 4 bits. 1, 2, 3, 4. So high state mean you are using 2 volt MOSFET. So high state mean VREF should be 2 volt and low state mean 0 volt.
There should be 0 volt. Okay.
Okay.
So you change the reference voltage 0 or 2 volt if you are using 2 volt MOSFET. So
Okay.
when you change reference, you can see the output. Okay.
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 Take this circuit first, and then the second circuit is this.
Full bit
I think
control.
this one is just take a few hours. You can make it really fast, and then make power control. This circuit might take some time, right? This circuit.
Yeah, it
Okay.
looks like a long one.
So first you have to make one delay.
How do you make one delays?
So I said use my circuit here, right? Um,
This one's the delay circuit.
yeah, for here I make some delay circuit test band.
Okay.
You can make delay circuit by using inverter. Do you know inverter?
Yes, inverter.
Investor,
Okay.
PMOS and inverter.
Okay.
What is inverter?
So you can Google it. Inverter relay circuit. CMOS. Where actually I have delay circuit, but I will find it. So ref another that. Then power whip control. Power whip control. Here is the delay circuit you make by yourself, and in library we already also have delay circuit. Wait. Here. Del mean delay.
Okay.
It is here is library. It look complex, but you can make it. You can test this, right? So you can make a test band to test the delay in here. Yeah, enable delay. You can check.
Okay, I saw delay.
So in here is about 600 picosecond delay gel. That is the delay one library. The delay two might be more delay, I think. I don't know. Let's check. Maybe double, right?
Yes.
So in here, so in library is only, so here it might be 7 picosecond. Here is 1.7. So you should check later. But around nanosecond delay, right?
Okay.
So if you need more delay, you can just make it in series, right? To make more delay. Okay,
Okay.
got it?
Yes.
That is a delay, and then so you can make this circuit, right? You know where is not gate, right?
Yes.
This is on in library. It's on in this library. ST50, right? In here,
Okay.
here in not gate, and here in NAND gate, and not gate. Maybe it will be inverter. There is inverter, not gate here. They call inverter. Okay,
Okay.
inverter, and NAND gate. Maybe this and this is the shortcut for NAND. Okay, NAND gate,
Okay.
and then MUX, we have multiplexer. We also have MUX. Okay,
Yes.
and what is okay? Reference is in the letter, right? Reference.
Yes.
It is this reference. Okay, let's try. Try to make this circuit and simulate it. How the reference will control the delay, right? You put in the clock and see how much delay. Okay,
Okay.
how much delay, and then I think it will not take much time. It's also take a few hours, and then the circuit is this is level shifter.
Okay.
This level shifter. Level shifter. Because in this circuit we use 1.8 volt, right? We store this block is on controlled by let me check. It is but here they are using 5 volt. Here is 5 volt library. We should find 2 volt library. We don't have, for example, this guy in our lab, he don't have 2 volt library, so he have to make by himself. For example, NAND gate, we have to make by himself like this. So I think you guys have to make this gate by yourself. This logic gate by yourself.
Okay.
So this is not difficult. So you can make not not gate, and you can make NAND gate circuit. Because you have not studied yet, so I will make and give you Okay, I will send you later.
Okay.
I will make because you need to study this logic gate to make, but now you have not studied, yes. So I will make it. And the level shifter circuit is here. This simulate this circuit. Okay,
Okay.
level shifter is not too difficult. Here is 1.8 volt, and here is 5 volt. I think, oh no, it should be reference. In here should be reference. Okay,
Okay.
so your this week homework is make 3 circuit. Okay, so after next week we can combine your owner the system together. Okay,
Okay.
Yes.
let's try to make all the circuit. Okay, see you.
See you.
Okay.
Bye.
Bye.
Good night.